Promethean board went out, and so we need to kind of quickly go over a few story problems, okay? So just remember that last time we learned how to graph exponential growth and decay, and we learned that an exponential function has the form y is equal to a times b raised to the x, where a is our initial value and b is our factor, okay? So remember that we had growth factors and decay factors. And we would know if it's growth if b, if our factor was greater than 1. We would know if it's decay if b is less than 1. Okay? So, let's look at these two functions and just determine right off the bat, are they exponential growth or decay? So, for example, really quick, f of x is equal to 3 times 2 to the x. You said it's growth, why?
Because it's greater than 1.
So it's growth because what is greater than 1? 2. Does the 3 matter? No. So because 2 is greater than 1, this is exponential growth. Very good. So how about this next one? F of x is equal to 3 times by 0.5 to the x. It's decay, and you know that because of y. 0.5 is less than 1, so it must be exponential decay. All right, very good. All right, so now we also learned these two formulas, but I didn't explain it very good because I got a little bit flustered because of my Promethean board breaking. So I just want to kind of retouch on this because, like I said, with that breaking, I was just like way flustered. Okay, so we learned that we have the exponential growth function for appreciation is a is equal to p times by 1 plus r raised to the t. So what I didn't explain last time, I just kind of rushed through this because it took me forever to write it on the board, but what I wanted to explain is this really is an exponential growth function. It's peeled back, the layers are peeled back, and we're kind of getting into the nitty-gritty of what makes up an exponential growth function, but it's the same thing. So do you see how p was the put-down amount? That's the initial amount, right? Isn't a the same thing as having a p, different variables, same thing, right? And then b is our factor, and we automatically were doing growth or decay factor. So for this one, 1 plus our interest rate, that would be our growth factor, right? So do you guys all see how it's the same thing, but it's a little bit like we're kind of peeling back the layers of what makes up these functions, okay? So then we learned that exponential decay, you'll know and you'll use decay if it's depreciation. It's the same formula except where we have 1 minus r, so 1 minus our rate of change, and then raised to the t. So now notice,
were we not supposed to know that already?
I'm going over what we learned last time.
Okay,
yeah.
Sorry.
No, it's okay. So then with exponential decay, guys, just like I said, it's the same thing. It's the same thing. It's peeling back the layers a little bit further. Because if we do 1 minus amount, we're going to have a b value less than 1, right?
Right.
Which would be decay. So do you guys see the connection there now, hopefully? I didn't make that connection last time. Okay, awesome. So let's apply these. These are really the easiest story problems you've ever seen. You should love them because they're really easy. They're literally kind of plug and chug. So looking at this example real quick, this is the old stuff. You don't have to take notes on this if you want to just watch. Just make sure you know what you're doing. So it says the amount of an old guitar grows at a rate of 2% each year. And if it is initially worth $300, how much could you sell it for in 15 years? So is this getting worth exponentially more or less? More. So we're going to use the appreciation formula. So A is equal to P times by 1 plus R raised to the T. And now we're just going to plug in everything that we know here. So P is the principal amount, the put down amount. How much was the initial value? How much was the guitar initially worth? $300. So we're just putting in $300 for P. And then times by 1 plus R, our rate, which is?
3.02.
It's 2%, and we have to write it as a decimal. So it's
0.02.
very good, 0.02. And then raised to the T, and how much time has gone by?
15 years.
15 years. So T time is 15 years. So you'll just type that into your calculator. 300 times by 1 plus 0.02 raised to the 15th power. And you get A is equal to, you can practice this and make sure you got it right, $403.76. Okay? So you got the guitar for $300 and now you can sell it for $403.76. Okay, let's do another one.
Someday.
These ones are really quick.
Oh,
Okay, so you buy a brand new Ford for $30,000. The second you drive off the lot, the value is exponentially decreasing at a rate of 14%. If you want to sell it in 5 years, how much will it be worth? So is this getting worth less or more?
Less.
Less. Exponential decay. So we're going to plug it into the formula. A is equal to P times by 1 minus R raised to the T. So then the amount it's going to be worth is equal to the put down amount. How much did we put down on the truck?
30,000.
It was initially worth 30,000 times by 1 minus R. Our rate is 14%. We write it as a decimal.
0.14.
0.14 raised to the T. How much time has gone by till I want to sell it?
5 years.
5. So once again, just type that into your calculator. Let's see how much this brand new beautiful truck is worth. 14,112.81. Very good. So that's why they say, you guys, an exponential decay of new car value is real. That's why they say, like, buy a 1-year-old car, because it's getting so exponentially worth less. That's why, like, if you buy a new car and you sell it a year later, you will lose so much money on it. And a lot of people actually do that. So, like, I actually bought my car. It was only a year old. It only had, like, 5,000 miles on it. And I got it for such a good price. And it was still a brand new car, but it hit, like, what they bought it for was, like, exponentially more than what I paid for it, only a year later, because it gets so much worth less and less. Okay, so last one, because we have to be able to kind of look at what we're given and then kind of adjust what we're trying to find. So what if instead of trying to find the amount in the end, what if we're trying to find this initial amount? So let's look at one more example and then we'll move on. How many of you collected Pokemon cards?
Me.
Yeah, me too. And the only reason I didn't even know it was like cool or not, but my grandma would give us Pokemon cards, and like we had this book, and like I had some that were worth a lot of money, and it was, I don't know, weird. So I never played Pokemon.
Did you
I'm not
ever
saying
get
it's
any?
weird, but I just didn't know how to do it. I lost the book, so I have no idea. I know, so I was just wondering. Okay, so let's read this problem and let's see what we're given. So it says, after 10 years, you have a Pokemon card worth $200. If the card goes up in value by 3% per year, how much was it originally worth?
Oh.
So is it getting worth more or less?
More.
More, so we'll still use the formula A is equal to P times by 1 plus R raised to the T. But this time, you guys, there's like, I can't teach because there's too much talking going on, so it's like I can't focus. I'm sorry, I'm trying my best, but it's really hard. Okay, so in this one, was our put down amount 200?
No.
No, that was the amount in the end, after the time, right? Good, so A was 200. So we're going to put 200 is equal to, we're trying to find P, right? It says how much was it initially worth?
Yeah.
So P is what we're trying to find. And then we have 1 plus R. Our rate is 3%, so 0.03 raised to the T. So the time is 10 years. Now look at this, 1 plus 0.03 raised to the 10th. Isn't that just a number?
Yeah.
Yes, so, okay, so how do we're trying to solve for P, so how do we get P by itself?
Divide by that.
Divide by 1 plus 0.03 raised to the 10th. Do it to both sides. 1 plus 0.03 to the 10th. So that divides out, and we have P all by itself. So you'll type into your calculator, 200 divided by 1 plus 0.03 raised to the 10th power. So the amount initially that this Pokemon card was worth was $148.81. So after 10 years, it went up to $200.
That's not
Okay.
a lot.
Not a lot. Better than nothing though,
That's
right?
still a lot
Yeah.
of
Okay.
money in the first place.
It
for a
is.
card.
Yes.
Well, if you wait 10 years, you could buy an extra pair of shoes.
That's true. Yeah. So wait another 10 years and then buy an extra pair of shoes. Good point. Okay, let's get to the new stuff, okay? So we're going to get to the new stuff. This is kind of like a kind of add-on to what we learned last time, kind of like pre-learn of what we're going to learn today, kind of, okay? So let's say that we were looking at something like this. So this is obviously an exponential function, but what do you notice that's peculiar about this one?
Think about how flat it is.
Yeah, you were saying it. Say it again.
The exponent has its exponent.
There you go. Now notice, we're used to seeing exponentials with just an x as our exponent. So now notice this is 2 raised to the x power. So I'm going to teach you right now how to just look at this. It's really no different than what we've been looking at. I'm going to have you look at this a little bit more in depth and then you'll see what to do. So if we ever saw something like this, just think about it, guys. Think about properties of exponents, okay? So this is the same thing as having y is equal to 3 times by 2 raised to the, what if I brought the 2 inside and then had 2 squared raised to the x power? By properties of exponents, is that the same thing? Because when we have a power raised to a power, what do we do with the powers?
Wait, you mean times them?
When you have a power to a power,
Oh.
power raised to another power, what property, what do you do? You guys know this. This is like secondary math, pre-secondary math 1.
You add exponents.
No, not quite. You guys, okay, I'll sing you a little song. I'll sing you a song of exponents. Oh dear, this is a good thing we're doing this. When you multiply, you add. When you divide, then you subtract. Raise a power to a power and you multiply. Power to a power, what do we do with the powers? Multiply. So is that 2 times x the same thing as that? So we're raising a power to a power. So we can rewrite it like this, right? Okay, hopefully we remember properties of exponents now. Okay, so this is the same thing as that. So, what is 2 squared?
The whole song you're saying were those all properties of
Yeah, they were all just properties of exponents. So when you multiply the same base, you add. When you divide the same base, you subtract your exponent.
Wow, I wish I learned that song.
Yeah. Yes. So this is the same thing as having y is equal to 3 times by what is 2 squared? 4 to the x. So do you guys all understand how you can rewrite these? Hey. Yeah. It's pretty cool, right? So you guys, you will see this kind of thing a lot of times on end of levels, and you might have saw something like this on the ACT and you're like, crap, what do I do? But just think of properties of exponents, rewrite it. Okay, so let's get to the new stuff. That was just kind of a, hey, by the way, type thing, okay? All right, so let's quickly just looking at this one real quick. First of all, how can we rewrite this? We just learned this.
2 times 2 to the third with x.
Like that?
Yeah.
Okay, so this is the same thing as having 2 times by what?
8.
8 to the x. So what is the factor? What's our factor, guys? Okay, it's growth. Okay, you're right. It's growth. How do you know?
Because 8 is bigger than 1.
So our factor is 8. 8 is greater than 1, so it's exponential growth. Okay.
Win.
All right. Let's do another one.
Oh, your song that you sang is on record.
Oh dear, you're right. I forgot. Okay, so looking at this one now, don't let this one throw you off, okay? So we have y is equal to 0.5 raised to the 2x. So I'm going to ask, what is our initial value on this one?
0.
I'm going to ask again,
1.
so think about it.
Is it
What is our initial value on this problem?
1?
0.5.
It's 1.
It is 1. Very good. So remember that you can rewrite this as y is equal to 1 times by 0.5 raised to the 2x, because always we technically have a 1 out in front, right? Okay, awesome. So good job. So let's rewrite this one. So we have y is equal to 1 times by 0.5 raised to the what? Second. And then, so we have y is equal to 1 times by 0.25 to the x. So is this growth or decay? Decay. I'm just going to circle it. And then what's our factor? 0.25. Thank you. Good job, guys. Okay, so we're all good with those. Okay, let's get to the new stuff. Okay? So what we're going to do today is we're going to graph shifted exponential functions. The good news is it's not a whole lot different. Literally one extra step. We learned how to graph last time, and you guys were all really good at it. So you don't need to necessarily write these steps down because we're just going to apply them in the next few problems. If you want to, just write quick. So this is the most important thing that you realize. So the general form of a function that's been shifted, if it's exponential, is f of x is equal to a times by b raised to the x minus h plus k. So this is the same for all functions, guys. We're kind of hopefully getting good at how shifted functions work. So the parent function would be a times b raised to the x, but now we're shifting it, so minus h plus k. So whatever is added up in the exponent with the x, that's our shift left and right. That works the same with all functions, right? And then you always go opposite. Yep, so if we had x minus 3, we would go right 3. Very good. So then this part, the part k, the constant that's added on the outside of the function, that would be our shift up and down. and that you go with this sign. This is the same for all functions, so this is not new, okay? So here are the steps to graphing the shifted exponentials. The first thing we have to do is we have to look where we're shifting left and right, where we're shifting up and down. And then that's your new starting point. So you're taking your origin and you're shifting it. Left and right, up and down, a certain way. It just depends. And then after that, graphing is the same. So we learned that after that, you plot the initial value, right? And then to the right, we multiplied by our factor. To the left, we divided by our factor. And then our fourth step is just to state the domain range and y-intercept. So let's just start really applying this because it doesn't make sense until we apply it.
Wait, so is the H the right one? I decided for sure to go to
Okay, awesome. Good to know.
What
So
part is-
also notice how and when I'm just going to elaborate on this drawing the horizontal asymptote. What was our asymptote last time? At y is equal to 0 on the x-axis. So now when we start shifting these things around, that asymptote is going to shift. So we're going to draw in our horizontal asymptote because that's going to help us because it's going to approach the asymptote, get really, really close, but never cross it, right?
Right.
Sweet, let's do it. I'm so excited. This stuff's fun. Okay, so first example. All right, so first of all, it's asking us, looking at this function, is it growth or decay? Okay, so this is exponential growth, and you knew that because why? 3 is greater than 1. Sweet, done with that. Okay, so now our first step is to find our new starting point. So we're going to look where it's shifting left and right, where it's shifting up and down. So looking at this, where are we shifting left and right? We're going right 4. And then we're going to go
Down 1.
what sign do we go with what's on the outside? So we'll go right 4, up 1.
Oh, so we're not flipping the outside one?
Right. So that's how it is with all functions. What's inside the parentheses or what's in the exponent. You'll go the opposite of that, but anything that's added on the outside, you go with the same sign. Yeah, good question. Okay, so our origin, we now are taking our origin, we're shifting right 4. So we're going right 1, 2. I'm going to move my little recorder over here for a second so I have some room. So we're going right 1, 2, 3, 4, and up 1. So boom, there's our new starting point, guys, okay? So there's our new starting point. Does everybody see my new starting point? So now we're going to draw in our horizontal asymptote. So this is our new x-axis here. Okay? Now what you're going to see me do, because it makes it a little bit easier, that part just became this part, right? We just made that our new origin. So you're just going to see me write the starting point as kind of like a little kind of X-looking thing to just remind us that we're just taking this and shifting it right there. Is everybody okay with that? Okay, so now it's easy from here because it's the same as graphing non-shifted functions. So guys, that's the only thing you have to do with the 4 and the 1. You can ignore it now. Pretend it's not there. And then the first thing we do is plot our initial value. So what's our initial value? So plot A, which is 2. So from our starting point, we're going up 1, 2. Okay? Now this is where we would do, I'm not going to do red. Okay, so now this is where we look at our factor. So to the right, we multiply by our factor. So to the right, we're going to multiply by 3. So we're doing 2 times by 3, which is 6. So this is where you've got to be careful, though, because now that we've shifted and shifted up, we are going to start from here, right? We're going right 1, but we've got to go up 6 points from down here. So we're going up 1, 2, 3, 4, 5, 6. So we're at point 7, which makes sense, right? Because if we weren't shifted, we would have landed on 6, right? We've shifted the point 6 up 1, which is 7, right? But you don't even have to think about it if you just plot it like I just did.
Wait, I thought you start at 2 and then go up 6.
No. Remember that you go start, if we were not shifted, we would be right here at 2, right? And then we would go right 1 and up to the point 6, up to the point 6. So that would be 6 additional from the very bottom, right? So does that make sense? Okay, so let's do another point to the right. So we're doing 6, and to the right, we're moving in the direction right. We're going to multiply by 3. Where are we going to end up? 18, right? So we're going right 1, but we're going right 1, and we've got to go up 18 points. Now that we've shifted, we're going to start down here and count up 18. Or you could just think about it. On a normal non-shifted function, we would be going over and up to the point 18. So what point will we be at now? 19. So we'll be at point 19. Or I could start here and count up 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Sweet. That's to the right. Now to the left, we'll divide by our factor. So to the left, we'll divide by our factor. So to the left, we're dividing by 3. So our initial value was at 2. We're dividing by 3. So how many, what is that? Let's do decimals. So 0.6667. So to the left of this, we're going left 1 and up 0.667. So like not quite 1. And then if we did one more point to the left, we'll take that and divide it by 3. So we'll be doing 0.6667.
It's 0.2222.
Good. So 0.222, so really, really small, or 0.3. So we're going left one more and up to 0.2. So we can draw in our shifted exponential function. Does everybody see how that worked? Okay, sweet. Questions? Okay, so now let's do domain. Domain on this one is x value, so left and right. Where's our function growing? Looking left and right, it doesn't matter how far up and down. Where is it growing this way? Negative infinity. You guys, in the x direction, this is negative infinity. And in this direction, where's it growing? Positive infinity. So it's growing, our domain is negative infinity to positive infinity. I'm going to write all real numbers. If you write negative infinity to positive infinity, that's fine. Range. Range is our y value. So with shifted ones, these ones, they're not hard. You've got to use your eyeballs though. You can see what our y values are doing. So looking at our y values, now we're looking up and down. It doesn't matter how far it's going that way or this way. It matters how far up and down this function is growing.
So it's going from 1 to infinity, right?
Good. It's getting really, really close to 1, and it's growing to positive infinity. So it doesn't ever cross 1 though, right?
Right.
We'll get really close to that asymptote, but it won't ever cross it. 1, and it's growing to positive infinity. And then our y-intercept is when x is equal to 0. So y-intercept is when x is equal to 0. So we could plug in 0 for x. So we'll be doing 2 times by 3 raised to the 0 minus 4, which is just what? Negative 4 plus 1. So you'll type that in your calculator. 2 times by 3. Make sure that you're doing 3 raised to the negative 4. And then plus 1. So if you type that in right, because 2 is not raised to the negative 4, so make sure you type it in right.
That's 1.02.
1.02. Looking at our graph, is that about 1.02? Crossing. Yeah. Look right here to origin. That's 1.02. Right? Awesome. Any questions? Yeah. Just, it's good practice for the test because they're going to ask you. Let's do another one. Okay, so looking at this one, is this exponential growth or decay?
Okay.
It's decay because, so it's decay because what?
B is less than 1.
Because 1/2 is less than 1. Very good. And now we're going to first say where our new starting point is. We're going to see where it's shifted left and right, where it's shifted up and down. So looking at this one, where are we shifted left and right? So we're going left 1. Very good. Left 1 and what?
Down 3.
Down 3. So from my origin, we're going left 1 and down 1, 2, 3. Then we draw in our horizontal asymptote. And then, like I said, I draw my new starting point as kind of like a little X type thing. Because remember, we're just taking this and shifting it left 1, down 3. So then from here, it's the same thing as graphing non-shifted functions. We can ignore the 1 and 3 as long as we work off of this and pretend like that's our new origin. Well, that is our origin. Okay, so now our first thing is to plot the initial value. What's our initial value? So we're going to plot negative 4. So from here, we're going down 4. Down 1, 2, 3, 4. We're at negative 7. Would that make sense?
Yes.
Why?
Because it's negative 4 and then the minus 3 comes in.
Very good. So the non-shifted one would be at negative 4, but we're shifting that down 3. So that'd be at negative 7. So it just makes sense, but you don't even have to think about it. I was just making a point. So we're done with that part, and now to the right, To the right, we multiply by our factor. So to the right, we're multiplying by 1/2. So we're at -4, right? -4 times by 1/2. That's the same thing as -4 divided by 2, which is -2. So to the right, we're going, and I'm going to start here because this is a shifted one, so you got to be really careful. We're going right 1 and down -1, 2. Let's do one more. So we're doing -2 times by 1/2. We're going to move in the right again, so we're going to multiply again. So that's -2 divided by 2, right?
Yeah.
Which is -1. So right 1 and down to the point -1 from the new starting point. Is everybody good at that? Now let's do it to the left real quick. So to the left, we divide by our factor, so we're dividing by 1/2. When we're dividing by a fraction, what are we really doing?
You flip the second multiply, sometimes it makes
Perfect. So we flip the second and multiply. So we were at -4, and then we're dividing by 1/2, or timesing by 2, same thing. So that's going to be -8. So to the left of our initial value, which was right here, we're going left 1 and to the point -8. So -1, 2, 3, 4, 5, 6, 7, 8. Which, yes, people are like, well, that's not at -8, that's at -11. Well, that makes sense. -8 minus 3 more would be -11. And that's, we could do another one. So -8 times by 2, right? -16 minus 3 more would be what? -19. So we're next to the left, we'd be at -19. So now we can draw in this exponential, decay function. It's never going to cross. Sorry, it was hard to draw on such a big thing. Okay, is everybody okay with the graphing on that one? So you guys, that still is decay because, yeah, it was really, really very, very small, but it got less small and less small and less small. Does that make sense? So it's still, looking from left to right, it started out exponentially small and got, it's hard to explain. But do you guys see how it's still decay because it started out large and got really, really small? Okay. So then domain is what? Domain is left and right. Where's our function going?
from -infinity to positive.
Negative infinity to positive infinity. So this is all real numbers. Range is our y values, so be careful with this one. What's our range on this one? What's happening up and down?
-3 to infinity.
Very good. It's getting really close to -3, but it's never going to cross it, and it's growing to negative infinity. We write that first. So negative infinity up to -3. And we put a parenthesis because it doesn't include it. And then if we wanted to find the y-intercept, and we do, the y-intercept is when x is equal to 0, so we'll be doing -4 times by 0.5, which is the same thing as 1/2, and then raised to the 0 plus 1, which is just 1, right? So 1, and then -3. You'll type that into your calculator. So that would be -4 divided by 2, minus 3. What do we get? Right, because -4 divided by 2 is -2. Okay, do you guys need me to do another one, or do you think you're okay? I think you're all right, yeah? Okay, so you're going to do problems 1 through 8. I don't. I hate them. Okay, so we're going to continue. Okay, so really quick, pay attention to what I'm teaching so that you can make sure you can do the rest of that. So we're going to talk about a very special exponential function, and you guys all know what it is. You've seen it in your math careers so far. So y is equal to e to the x. So e to the x is just an exponential function, a really special one. So a lot of times people mistake e for being, they think it's a variable. E is a number. So e is actually a number. It's approximately, just so you know, just for a fun fact, e is approximately 2.7. So fun fact. So looking at this, we've been seeing exponentials in the form y is equal to a times b raised to the x. So e is just a number, right? So really it's just an exponential function. What's our initial value on e? 1. So this is the same thing as y is equal to 1 times by e raised to the x, right? So do you guys see how it is just it's an exponential function, a special one though? Okay, awesome. So now we're going to find values. It just wants us to actually evaluate some values of e to the x. So we'll literally use our calculator. So it says find the values of y is equal to e to the x, rounded to 4 decimal places. So e to the 4, you'll literally just type it into your calculator. You'll go, so now notice right here on my calculator, see this is the ln button. Now notice written in little writing is e to the x, so you've got to do second ln, and that makes it e. So we're doing e to the, did I say second power? My example, 4. So e to the 4th power, and then I'm just going to get out of there and say enter. So 4 decimal places is 54.5. Okay, so writing this down, we get
54.5982.
and we're going to 4 decimal places, so
Wait, isn't it 0.5982?
Yeah, 54.59.
0.5982. Okay, worst handwriting award goes to me. All right, so now I would just quickly do problems 9 through 11. You just saw those. It'll literally take you 2 seconds. So we'll quickly do those, and then I'm going to keep going.
Wait,
Okay, so now you'll want to write down this second. So we're dealing with E today, the special thing that I'm just showing you 2 things real quick to kind of, put into perspective when we use E, okay? So we're going to be talking about compound interest, and today we're going to be dealing with, you only need to write this one down because this is what we're going to be doing today, but I just wanted to make a point so in the future you're not like, well, that doesn't make sense. Okay, so compound interest, and this is found in real world situations all the time. You'll go to a bank and they'll say, we'll offer you this interest rate, and it's compounded yearly. So that means you get interest once per year. If it was compounded bi-monthly, that would be twice a month you're gaining interest. You know what I mean? So do you see what I'm saying? So like, if you were compounded monthly, if you were gaining interest monthly, how many times in a year would that be? 12. So you would get interest 12 times a year. Does that make sense? Okay, so if that was true, if n is measurable, so n is the number of times it's compounding in a year, we would use this top formula. But today we're going to be using this one because we're going to be dealing with compounded continuous interest. So like I said, we could sit there and split n up. So what if I said 3 times a month? Then we would use this formula, right? But what if a bank said to you, you know what, I'll do better. I will give you interest all the time. At any given time in the day, I will continuously give you interest. Wouldn't you rather have continuous interest than once a month? Yeah, so a lot of times they'll kind of flash that at you. We'll give you compounded continuous interest. So at any given time, you're getting interest. But really, depending on the interest rate, it actually won't make a huge difference depending on how large the interest rate is. But interesting. So if you ever see the word compounding continuously, we can't measure n. How do you say continuous? How do you split up always at any given time, every second, every millisecond? You couldn't, you know what I mean? So then you'd use the formula A is equal to PE raised to the RT, so PERT. A is equal to PE to the RT, some people say it PERT. Okay, so A is the amount in the end, P is our principal, our put down amount, and R is the interest rate. We write it in decimal, and we just learned that E is just a number. You'll use it in your calculator, you'll type in E, but remember E is just the number that's approximately 2.7. You won't write 2.7, because E is, you gotta use the full decimal E. You'll just use your calculator, use the E button, just like we did in the last problems, okay? So let's do a few examples. These are really easy too. You'll just plug and chuck. So I'm gonna do a few examples really quick.
wait. Never mind.
Yes.
So is the top one raised to the NT or is it to the RT?
Yeah, that's the NT, sorry.
Okay.
Yeah. But like I said, this one you guys we're not gonna do today because we're focusing on the special one E today. I just wanted to make a point so that you're like, you didn't say anything about that when we start doing, we're going to have a full day of story problems, we're going to see this, but I just wanted to say, when n can be measured, you can't use this, because it's not gaining interest at any given time. E means it's exponentially at any given time gaining interest, okay? So we're just going to use this formula, it's plug and chuck. So first example. The bank offers a 2% interest rate compounded continuously. If you ever see that word, compounded continuously, you say, I'm using PERT. So I'm going to automatically write down my equation. A is equal to PE raised to the RT. And now we're just going to plug in what we know. So it says the bank offers a 2% interest rate. So our R is going to be, how do we write 2% in decimals? 0.02, and it says compounding continuously. That's the E part. How much would you have for college in 3 years? So what's the time?
3 years.
3 years. If you put $500 in the account, so how much did we put down? 500. Sweet. So A is equal to 500 times by E raised to the 0.02. That's R times by T. So times by 3. And then you'll type that in your calculator. 500 E raised to the 0.02 to the third. Times 3. Okay, so I'm going to pull up my calculator. So I'm going to pull up my calculator, and I just said it's 500. So everybody watch. 500 times by E, so second ln, so I can get my E going. And then it was what was my interest rate? 0.02 times by what? 3. Get out of your exponent, hit enter. $530.92. So we didn't gain that much money. Looks like college isn't looking so good. Okay? So like the bank made it sound really cool. $30 is better than nothing, but really not that cool. $530 and whatever, what did I say, 92 cents. So we made $30.92. Yippee, yippee. Okay? Awesome. So you're right, about $10 per year. Okay, better than nothing. All right. So this is another one. It's going to be worded really different, and I know many of you won't be able to do it unless I do an example similar. So let's think about this one together. So it says, how long would it take you to triple your principal at an annual interest rate of 25% compounded continuously? Automatically, when you see the word compounded continuously, you say, I'm definitely going to be using PERT. So A is equal to P-E raised to the RT. So this was just an example. So it's saying, how long will it take you to triple your principal? So like if our principal was $10, how long will it take us to triple that? It would be 30, right? For example, right? So I'm just showing you. So really, you're like, well, we're not given a whole lot. So let's think about what we're given. So we are given our R, right? R is what? 0.25. 0.25. T is what? How long would it take you to triple your principal?
Yeah, we're trying to find that out.
That's what we're trying to find. Good. I'm glad you were able to see that. That's what we're trying to find. Well, what the heck? We don't know A, and we don't know P either. But really, with these ones, you could say, well, what if our amount, in the end, what if our principal amount was 1? Then when it was tripled, what would it be at? 3. And then we only have one unknown, right?
So basically we could put
T will work the same. Yeah, we can put as long as you've tripled it.
Yeah.
Yes. Yeah, so I'll just always use 1 and 3. So we could do 3 is equal to 1 times by E raised to the 0.25 times by T. So watch carefully, guys. We're trying to solve for T. So we're trying to get T by itself. So I divide by 1. This is counterproductive because we know how 1 works, but I'm just showing you the steps. So we have 3 is equal to E raised to the 0.25 times by T. So this is where people are like, how the heck do we get this T out of the exponent? It can't just magically float down. Okay, so now I'm just going to tell you something new. So just like tangent, to undo tangent, you would do tangent inverse, right?
Yeah.
To do undo sine, you would do sine inverse. So the inverse of E is ln. ln, the natural log. So we're going to take the ln of this side. If you do that to this side, you've got to take it of this side. So over here on the left, I have the ln of 3.
How do you even type that in your calculator?
There's an ln button. Look at right there on the left, there's an ln button.
But would you do ln and then 3?
Yep. So we have ln of 3 is equal to our ln. I said it was an inverse of E, so it undid that. And now we just have 0.25 times by T. ln undoes E, just like sine inverse undoes sine. Kind of cool. So now how do we get T alone? Divide by 0.25. Divide by 0.25. So we have T is equal to
4.39 years.
good, 4.39 years. Okay? So ln undoes E, and to type that into your calculator, like I said, you'll just go ln of, what was it? Sorry, gosh. ln of 3, you've got to close your parentheses, and then divide it by, I'm going to put this in parentheses just for my own comfort, 0.25. And then hit enter. Okay, awesome. Do you guys all get it? Okay, that's it. You guys can do the rest of that worksheet.